Hello everyone, thank you so much for attending this session. I am Behnaz Ghodoosipour. I'm a PhD candidate at the University of Ottawa, Canada. Today I'm going to present a part of my PhD thesis project titled Dam Break Wave Loading on Nearshore Pipelines. This project has been conducted in collaboration with WASEDA University, Japan. Here is the outline of my presentation. I will start with an introduction and talk about the motivation and objectives of this study. I will talk about the experimental study, which has two parts, one conducted at the University of Ottawa and another one in WASEDA University. And I will show you some of the results that we got and discuss the results. I will end my presentation with some concluding remarks. So, as for the motivation of this study, pipelines are being used for several purposes, such as transmission of oil and gas, as well as transport of wastewater and depositing them into water bodies. When it comes to the design of pipelines, several parameters and forces are involved, and one of them is the hydrodynamic force. A new topic in pipeline design has emerged recently, and due to the increasing number of extreme events such as tsunamis and storm surges which we are noticing every day nowadays, and therefore there's a demand for guidelines and design specifications for pipelines to be able to resist such extreme events. Here you can see some examples of some of these devastating events and some damaged pipelines as a result of such events. There are several guidelines available which make suggestions for the design of structures to be able to withstand and resist against extreme events such as tsunamis. Among them, FEMA introduces two main hydrodynamic forces, which play important roles when it comes to the design of the structures, mainly drag force and lift force introduced by the formulas you can see in this slide. Also, ASC 7 has introduced a new chapter 6, which is on tsunami laws and effects, and it emphasizes on the need to investigate tsunami laws and pipelines located in tsunami-prone areas. So, the objectives of this study are investigating dam break flow hydrodynamics and its change in the existence of horizontal pipelines installed in its flow path, investigating the effect of initial bed conditions as well as initial flow conditions on induced forces on pipelines, and to also investigate how the bed slope will affect the induced forces. This study suggests and proposes force coefficients for various flow conditions and pipe configurations for optimal pipeline design, and recommendations from this study will be used in the assessment and improvement of the current tsunami design guidelines, such as in ASC 7 Chapter 6. Here's the experimental setup that we use at the University of Ottawa experiments. Some of you may have seen these experiments and some of the results we received in ISCCE 2018. The tests were conducted in a dam break flume, which is 30 meter long with 8.5 meter long for the main part of the flume. We have the pipe installed almost 6 meters downstream of the swing gate, and by opening the swing gate, the broken tsunami wave is generated, will impact the pipe, and we have an embedded dynamometer which measures the time history of the force. Different instrumentations include wave gauges for measuring the water level, as well as ADV for measuring the flow velocity. And different parameters were changed and tested during this test, including the gap size and also the level of submergence of the pipe in the case of wet bed condition. Here you can see some photos from the actual flume and the instrumentations, including embedded dynamometer. Here we have some videos showing the experiments from two different angles for a better understanding of the experiments and how they work. And here are some results from the experiments. These results are for the case of dry bed conditions and in varying gap size. Results suggest that in the case of smaller gap ratios, the impulse force is considerably larger, and also we have a more considerable negative lift force in this case. The total force shows to be in general larger for smaller gap sizes. In order to be able to study the effect of bed slope on the induced hydrodynamic forces on the pipeline, a new set of experiments were conducted in the wave flume at WASEDA University. The flume is 30-meter long in total, with 6-meter long reservoir and a 7-meter long, which is the main part of the flume. A horizontal pipe is installed using the setup that you can see in this figure here. The dynamometer is connected to the pipe from the top in this study and in these set of experiments. Again, we have wave gauges for measuring the water level and testing different impoundment depths as well as different sloped bed. We were able to perform a comprehensive study. Here we have a sample video for the case of the 1/20 slope. You can see the slope bed here, and you can see how the dam break wave is propagating and impacting the pipe. In this study, we used high-speed cameras for measuring the flow velocity as well as monitoring how the wave impacts the pipe. Here we have a video from the high-speed camera, which gives us a clear understanding of how the wave impacts the pipe and how it moves around the pipe. So we tested 3 different slope beds, 1/10, 1/20, and a combination of 1/10 and a 1/40 slopes. Results from the study shows that the drag force in the case of flatbed is larger than the 3 other tested slope beds, and as the slope increases, the magnitude of the drag force decreases. As for the lift force, it was noticed that the peak lift force in the case of flatbed is larger, whereas changing the slope bed does not have a significant impact on the magnitude of the lift force. The main result from these two combined set of experiments is a curve for resistance coefficient versus fruit number that we suggested to be included in the ASC 7 chapter 6, and it was accepted to be included in the guideline. So we were able to test a wide range of flow regimes and fruit numbers, and the curve suggests that in the case of supercritical flow, we can consider a constant resistance coefficient close to 1 for the case of horizontal pipelines, and in the subcritical regime, as the fruit number decreases, the resistance coefficient increases. The same type of curves were suggested for the lift coefficient, where we have a curve for the positive or upward lift force, and another one for the negative or downward lift force and lift coefficient. Here are conclusions from this study. For the flatbed experiments conducted at the University of Ottawa, we concluded that in the case of dry bed condition, at the beginning of the bore surge, larger drag forces are observed for smaller gap ratios. When the pipe gets fully submerged, a smaller drag force were observed for smaller gap ratios due to vortex shedding suppression, and larger lift force were observed for smaller gap ratios due to the asymmetry in pressure distribution. In the case of wet bed condition, smaller level of initial submergence resulted into larger impulse force, and for the cases where the pipe was fully submerged, no impulse lift force were observed. From the test performed on slope bed at the University of WASEDA, drag force showed to be decreasing with an increase in the beach slope, and the peak lift force showed to be significantly larger in the case of flat bed comparing to the cases with the slope beds. A study suggests force coefficients. For resistance coefficients, the values suggested were between 1 and 3.5, and for the lift coefficients, values between minus 2.8 and 2.8 were suggested. These results, together with the curves that we saw with each other in previous slides, will be included in ASC 7 chapter 6. Here are the references used in this presentation. Thank you very much for your attention. I will be happy to answer questions.